To launch our session, please welcome Casey Dreyer.
Thank you, Dwight. Thank you, everybody, for coming to join us and talking about getting humans to Mars today in our Planet Fest 2021. I'm very excited to welcome our primary guest for today's session, Rick Davis. He's the Assistant Director of Science and Exploration in the Science Division at NASA headquarters in Washington, D.C. Rick has worked both in the human exploration side of NASA and as the kind of the HEO representative within the Science Directorate for a number of years now. Rick, thank you so much for joining us today.
Hey, thank you. And thank you to everybody who's joining. This is really great. I'm looking forward to the conversation.
So just to kind of outline my vision of this, I've got like a thing to write with. I'm taking notes. I don't want this isn't going to be a presentation by Rick telling you about Mars. This is going to be us talking about getting humans to Mars. And really, we want to get a ton of your questions. This is a breakout session. Everyone here is here because they want to hear about humans to Mars. So let's nerd out on this. If you have crazy questions, if you have great questions, if you just wanted to know about what NASA's working on or how we will get humans to the red planet, this is your opportunity to ask the questions and see if we can stump Rick on some of these things.
I was going to say stump the chump.
So don't be shy to ask your question. In the chat room or in the Q&A on Whova, we'll get to as many as we can in the next hour. But being the host, I get to have, I guess, privilege to begin with this. So let's start with this big picture thing. And I kind of want to start like, Rick, why haven't we sent humans to Mars yet? Why are we still talking about this as a future goal?
So I love that question. And I would say that there are a couple reasons, in my opinion, about why we haven't done that. It's not like we're not advancing. We've done amazing work on the architectures for understanding the pieces that we need to do to go to Mars. But a lot of times we go to the end state where we're, all of a sudden magically on Mars with 500-day stays of crews and that kind of thing. And the problem is we're now getting smart enough to actually start asking, what are the things you need to do in close to make that a reality? So we understand the problem. But then the key point is that now we need to start doing, and we are, the next pieces to enable that. In fact, Casey, if you have that chart, I'll just kind of quickly walk through those major pieces and then talk to some of the pieces that really we are working on heavily right now so that we can actually ensure that we are progressing towards Mars and landing humans on Mars. So this is a picture of all the major pieces you need to have to go to Mars. And it's a lot. So you have a launch vehicle, a heavy launch vehicle to push big stuff up. We're showing the SLS and Orion there, and that's a key piece of it. But really, you also need a lot of heavy lift capability, which we are now seeing emerge, not just with with commercials, but even internationals are developing major capabilities for pushing stuff up into space. And then you have to return, of course. So that's the Orion capsule where you can actually withstand the heat of the US. Those capabilities are really pretty far advanced right now, and also if you add in the commercial capabilities that have come online. Now out come the pieces that we are less advanced on. So there's the Mars Transfer Vehicle. This is the vehicle that goes all the way from the Earth-Moon system all the way out to Mars. This is the big cool ship in the Martian, but and actually we work closely with them on that. But this is your mothership. There's a lot of work that needs to be done on that, particularly in the area of propulsion. We can get there with the current chemical systems, but it ends up being really big. We really are beginning to realize that one of the ways to reduce the risk of loss of mission or loss of the crew, even worse, is to get them there faster. And so we are doing a lot of work on nuclear propulsion capable options right now to help make sure that that vehicle can get out there instead of a typical Mars mission of 3 years, maybe even down as low as 2 years. And that may not come online immediately, but with something that strategically we're looking at a lot. We also need to realize that getting out to Mars, a big part of it is cargo and getting it out there. And you kind of got to think a little bit like the way we do things in ports on the ocean. So you will have ships that are designed for people to go, and those are actually aircrafts, right? Typically, but they can go by ship. But then you have these slow moving things all the way down to tugs that can push cargo very efficiently with technology like solar electric propulsion out there. And that's going to be a key for reducing costs and making these missions more affordable. Then you got the comm, of course, but then you got land. And just to give you a sense of it, on Thursday, we're landing the Perseverance. It's a 2 metric ton lander. Human class landers are going to be in the range of 20 metric tons. And that's a big deal. And they may be 25 metric tons to get down there. And it's a whole different ball game. You can't use chutes. We already know that those don't work. So a lot of the techniques like sky crane and chutes that we're going to use on Thursday won't work for these missions. We're going to need supersonic retropropulsion, which is actually SpaceX has been doing a lot of innovative work in that regard. Are going to be critical for landing these big things down there. And then when you get down on the surface, you got to have a habitat. I personally, I'm the science mission director, and I hope to God there's a pretty cool laboratory, because you don't go all the 220 million miles from here and not have the amazing solar system class. Notice I didn't say world class, solar system class science. And so you better have a laboratory, and we better be looking for signs of life. And you got to get around, and then you got to have a suit. And the suits are not the space suits we've been using to date. These are going to be different because, first of all, the current suits right now on the space station, if you go into those suits, it takes about a month of activities. It's not all that whole month, but it's spread over a month. We call it the road to get a suit ready. They're too difficult to maintain. They weigh too much. And those things weigh about 300 pounds, roughly speaking. And you are not going to walk in a one gravity or 1/3 gravity environment in 300 pounds. That is going to exhaust you. So getting that weight down to something kind of like what you might have seen in The Martian is going to be critical. It has to be able to hop into it all the time. There could be biology on Mars, and so we got to make sure those suits are tight as we can make them. They got to handle the dust environments, and that's really hard on the suit. On the Apollo program, when they went out on the moon, the dirt, or regolith as it's really called, is basically glass shards. And on Apollo 17, they almost sliced through a suit and could have potentially killed somebody had they done another walk on the moon. And we got to make sure that doesn't happen on Mars and that they can last a long time. Then ultimately you have rovers, and you got to come home, and the Mars Ascent vehicle. And one of the cool things about this mission that lands on Thursday is it is the first of a 3-mission sequence that is actually going to include the first Ascent vehicle off of Mars. And so all these pieces, and the last piece, which is a piece that I personally work on, is near and dear to my heart, which is reconnaissance. And that's all the things you got to know before you actually send humans there. And it's not just the things you need to know for engineering purposes, like where's the water so I can make propellant for that Ascent vehicle to come in there. But it's actually, it's also about what do you need to know about the science sites that we want to go to. So for example, increasingly many of us are beginning to realize that one of the coolest places to send human beings is where there are subsurface ice deposits at Mars. Because if there is life at Mars, it is probably very near or in these ice deposits. And having crews potentially bring back ice cores like they do from Antarctica will be totally cool. But that means you got to know where the ice is. And so there's some significant gaps in our knowledge of where it is. But those are all the pieces. And just to summarize some of the key ones that are really hard, that we are working super hard to get that development down. First of all, I mentioned the propulsion for that Mars transfer vehicle or mothership. That's a big one. Next one, landing those 25 metric ton vehicles is a big one. And then thirdly, that reconnaissance piece that I talked about, because you can only go to Mars every 26 months. And there are certain serialities. You need to know this before you send this mission. You really have to get on that sooner than later if we want to have answers to these questions that allows us to pick an exciting, from a science standpoint, and safe location for humans to land there. And that hopefully gives you a little sense of the challenges. But those are the big parts in general of doing a human mission to Mars. Anyways,
That's it.
in case I just want to give that overview in case it helps spark some additional questions.
Thanks, Rick. And I saw a few people saying that they were getting a bad echo from me. So I switched my microphone. So we'll see if that improves it. So Rick, you can still hear me okay? Okay.
I can hear you just great. Thanks.
Okay. So, I mean, just looking at this, I'll just leave this slide up for just a little longer. What really strikes me is the amount of stuff that we need to make to get humans to Mars. And I think that to answer kind of that big question, why haven't we already gone? That kind of is part of the response, right? Is that stuff in space is, I mean, it's hard to make things that work in space, and hard to make things that keep people alive in space. And having, you know, this much mass to get to Mars just takes a lot of launches or big rockets to get them there. And all of this, I mean, again, like, why do we need cargo tugs? Why do we need these comms networks? Why do we need these big transfer vehicles? Because Mars is just really far away and it just takes a long time to get there. I mean, is it as simple as that? That just Mars is really a far way to go, and that's why it's so hard to
I think it's a big part of it. Another part of it that I think is critical is that, so when we originally looked at going to Mars, we were trying to figure out all these pieces, right? So now comes the next part, is how do you sequence them in a way that allows you to not just buy down or develop the capabilities that are allowing you to get there, but also do it in a way that doesn't break the bank. So you step your way into it. So for example, it could be that the initial mission to Mars could be an orbital mission. That saves you from having to pay for all of that ground infrastructure right at the beginning. Or it may be that we do short stays to begin with, because then you don't have to have everything there. And there's some people who will go say, well, you know what, you're going all the way to Mars and you're not going to land, or you're only going to stay for a little bit of time. That seems like a waste of time. And my counter to that is I worked the space station for probably 18 years. And I will tell you, we kill for crew time in space to do amazing science on board that vehicle. And it just goes around and around the Earth. In this vehicle, that mothership, we're going into a region of space, a region of the universe that human beings have never, ever been in. And our potential to learn is going to be massive, whether you are in transit there, in transit back, in orbit, or on the surface for a short stay. And you know what we learned with space station is we built up to those capabilities. The original space station was just tiny little 2 small Russian modules, and it is now a football field of modules. And the key there is that for successful exploration, whether it be to the space station or Apollo or even Antarctica, or previously, they tend to build up capabilities, do it safely, and then learn what really works. And it's that incremental assessment that we're getting so much smarter about now. And that's actually what I would call the next phase of this to really make it happen, is we're learning how to sequence this in a way that is safe, that gets it done, and frankly, getting it done is, a lot of people say Mars is hard, and that's a euphemism for Mars is impossible. I completely disagree with that, having been involved with this. Mars is a challenge, but it is not impossible. But you have to know how to sequence it in a way that actually allows us to be making progress year by year and then learn the way. And the last point I would make is that there is no total plan for going to something as audacious as a second planet. But we need to realize is that all we need to do is figure out the next 2, 3 steps, do those, and that path will literally change as we get smarter. And that is successful exploration. When Lewis and Clark set out, they didn't know wherever they were going completely because there were no maps, but they iterated and they successfully did that. And I would say that really the great successes in space have really pretty much followed that paradigm.
Right. And so I'm going to pop out of this view now. I'm going to stop sharing my screen so you can see us again. And if people need to see a reference, let me know in the chat. We'll come back. So just again, to build on this, I liked what you said about phasing, about building pieces out. Because again, you look at I think the space station is a really good kind of pathway where, you know, I was saying in an earlier discussion about kind of the politics of this. Reagan announced space station freedom during the State of the Union in 1984. And the first piece launched, I think, what was it, 97, 98? And that's a long time to get to that point. And then you spent the next 15 years building it out. And so, you know, we can do long-term multi-decadal human spaceflight projects. It's just you have to build that kind of coalition to commit to it. And so I think looking at this plan, you can see we're kind of still on these really early stages, right? The heavy lift part where you have here the Space Launch System, maybe we'll have, you know, or Starship and Super Heavy coming in to be able to provide similar things. And we're practicing about understanding Mars a little better. Something that was really strikes me about this, you know, it's like we still really don't understand so much about Mars to begin with, about how to send humans there safely. I think about what happened to the wheels of the Curiosity rover, where they just were torn to shreds. And this was like what the fourth rover they had sent, or what happened that with InSight, that they couldn't dig its mold down into the surface because the soil is completely different. Right?
That's right.
And so how much is that a problem for planning for humans to Mars, that we still need to understand so much about the environment?
So I love that question. It's a fantastic question. And I would say part of learning to step it is actually being really careful about paradigms. And let me give you an example about that, okay? So I sat in the Houston Flight Control Room for many years as a Capcom. And I will tell you, if when you're sitting in that flight control room, if you have one thing in your head, and it is this: in space is dangerous, on the surface is safe. What people forget is that when they say on the surface, they really mean on the surface of a planet that we have evolved on for billions of years. It is like designed to create and sustain life despite even stupid things that we do. You know, and I am shocked at the number of people who will take that paradigm and apply it at Mars and say in space is dangerous, on the surface is safe. And so I love this number, which is that we count human days. So like if there are 3 people in space for a day, that's 3 human days, right? And so right now in space, human beings have, I don't know if I can see the chats here. I usually ask this as a question, but so I won't do it as a question maybe. But I would like someone to guess, and maybe you all could read it for me, how many human days humans have in space right now?
All total?
All total. Just
In
a guess.
history.
I want to get people thinking about approximate
How many human
numbers.
days in space, everybody? Let's see if we can get some responses in the chat. 2,600 I'm seeing.
Okay. Any
Anyone
others?
else? It's okay. No wrong. Well, there's all wrong. There's lots of wrong answers, but it's not a bad.
Okay.
It's okay if it's a wrong
Okay.
answer.
So
18,000, 10,000, 2,000.
Okay, the 18,000 is closer. Yep.
Okay.
So it's 65,000 human days in space. And now I'm going to ask the obvious question of how many human days we have on the surface of an alien planet that we have only sent robots to, and now that answers by definition 0. And so the point being is that you have to be very careful about that paradigm. And then why is this important? Is because even your definition of a safe haven changes if you answer the question, ask the right question. I would argue that the safest place on a Mars mission is actually in that Mars transfer vehicle, that mothership, because you will have spent most of your time in there. It is built, it is a second generation version of space station, actually. We know how to keep those machines running in a way that keeps people alive. We still are finding out about basic things with rovers like wheels, like you had mentioned, Casey, that are crapping out on us because we just don't know how to work in that kind of environment. And there's going to be a lot of learning like that. So not only is it stepping, but it's being careful about the paradigms that we apply. And if we do those things in a way that really reflects the realities of what we're dealing with, we're going to be actually at Mars before most people know it. And they're going to be shocked. Some will be shocked, although kids in school right now won't be, that we're actually landing human beings on our next planet.
So I want to start getting to some submitted questions here, because we're having a ton of questions come in, and we only have 40 more minutes to answer your questions. So we will get to as many as we can. So let's start with the top highly most voted. So it seems to be around radiation. And so what's the current understanding about the health consequences of radiation, and how do we mitigate those for the safety of astronauts going there and back?
So There is a lot that we can do to mitigate it, and it's not an unknown thing. When we send off probes, we have sent dosimeters on them. We know what the radiation environment is on Mars, and these are manageable problems. I would assert. I think the community is rapidly going. So let me tell you about some of the challenges. So then we can talk about what we're doing to mitigate them. So when you are in the space station right now, which is at about, what I forget, it's about 230 miles up or whatever, you're below the Van Allen belts. And that's one of the things that this planet that is designed to create and sustain life. And it is magic in my book. It has these Van Allen belts that just trap really nasty, high energy, destructive particles from the sun. And then also what we call galactic cosmic rays that are coming in from a way out in space that are extremely high speed particles. And those things, when they hit your cells or when they hit your DNA structure, there's like shooting a bullet through your body, a very microscopic bullet through your bodies. And so when you're on the space station, you still get some of this radiation. When a crew member's in there, they'll get a radiation blast going through their eyeball, and light will flash in their eyes that we don't see on this planet. They do see it up there. And when you're heading past those Van Allen belts, you're talking a different radiation environment. Now, how do you manage it? Well, let me add one thing. So deep space, when you're in the mothership, that's going to be an issue. There are ways to manage that. So, for example, you can put your water. Water's a really good thing for stopping some of that radiation. High density materials, which weigh a lot, so they're not so ideal. But you can do really clever things like what damages a human being is the total radiation. There is something called acute radiation dosage, which is like if you're sitting next to a nuclear bomb going off, for example, that's an acute radiation dosage, unless you're vaporized. but
it's a bad day no matter what.
Yeah, that's a bad day. But the point being is that what really kills a lot of people is that they get this massive dose that is just the body just can't handle, and that's an acute dose. But that's not what happens in space, generally speaking. What happens in space is that you just get this cumulative dose, which has damages and affects things like, really the big thing is for people who are childbearing, it affects eggs and sperm and that kind of thing. And that really can affect having children, which are very dense things, dense biological entities that are really subject to that radiation. But you can do smart things. So there's acute radiation and then there's total radiation. And total radiation can be reduced by just reducing the total exposure. So when you go to sleep at night, you sleep in a sleep station that has got a lot of water around it and a lot of dense materials, not the whole spaceship, but you do it in that area. And that way we reduce your dose that you get at night. So that and then the total dose actually stays below a thing. There are ideas about creating essentially a Van Allen belt or magnetic field around the spaceship that are being looked at to actually divert those particles so that we can protect that way. And then when you get to Mars, the situation is actually better at Mars, because at Mars you have an atmosphere that is protecting. You do not have a magnetosphere, which is those Van Allen belts. Mars doesn't really generate Van Allen belt equivalents, but it does. At nighttime, the planet is between you and our sun, and so that blocks a lot of radiation right there. That atmosphere, even thin, blocks it. And then there are some really cool ideas that are out there. There's some work that the UAE has been doing, for example, that is looking at having people sleep underground at night. There's some people who talked about taking dirt and covering the modules. My retort to that is, you don't go to 220 million miles to have yourself covered in dirt. You're going to want windows. You're going to want to understand the environment. You want to be participating in it. But the idea of sleeping at night is really cool, because then you can actually reduce that sustained dose down and make it more manageable. And tricks like that are the way we're beginning to realize how you manage this sort of thing. In general, I don't think anybody thinks that one mission is not there, but all of us who are thinking Mars are imagining people actually starting to live there, right? And then you start begging a question that was actually in the pre-questions for this event, which is like, how long can human beings live there before, with the radiation environment? We don't know. It depends on how successful we are as we step our way into managing it. But what we do feel like is we can manage that, at least for a single mission. And then finally, one of the last thing I would say about, and I don't mean to go on too long, which is that there has been a fair amount of discussion about sending older people simply because they're past childbearing years where, and that gets that risk to a future generation down somewhat. I don't know if that's really going to cut mustard in the end, but it's definitely some of the ideas that are being looked at. That's a really cool question. Thank you.
Yeah, how much is this a problem that we impose on ourselves? I mean, obviously, societies, and particularly for an organization like NASA, I feel like it has this almost like a burden that it represents the nation, it represents our ideals, it represents our values.
Yeah.
And so we have to value life of the astronauts, safety of the astronauts, the people who are doing this. But how much is it a self-imposed requirement about radiation exposure? Like, could we change that and do an informed consent with astronauts to say they accept the risk of that potential damage? Is that under consideration, or are there deeper issues that prevent something like that?
I think that's we're definitely looking at easing the radiation limits. That's part of the trade space, which probably involves what you're talking about. I studied history before I went to aerospace engineering, and I love one number. I grew up in the state of Virginia, and I always loved going to Jamestown. It's an example of a perfectly crappy landing site, by the way. But the point being is that between 1607 and 1623, I think they had about 20,000 people go to the Virginia colony. And at the end of 1623, only 2,000 of them were alive, because they didn't know how to do farming. They didn't know how to handle a lot of things there. And so they basically had a 90% mortality rate. And I'm not saying that's what you want to be doing, but I'm saying those risk tolerances, they're different for different ages and different societies. And I would even say different entities, like a corporate entity may have a whole different risk profile.
Right. I think that's always an interesting, like we talk about, so, we can talk about SpaceX and kind of what they're trying to do too, but that's kind of what I was getting at when I said that NASA has this additional burden of saying, we're a reflection of the US. NASA is a reflection of the United States. It's a symbol for the United States. And therefore, what failure means to NASA, or what death, astronaut, mortality or consequences, means something different than an organization because it's a symbol. And we shouldn't, in a sense, allow or have the same kind of risk factors for a national symbol, in a sense. But that just makes things harder in some ways. And then the other question, I always think about this too, when you talk about like the risk factors for, when the era of exploration prior to, of expanding, the colonial efforts to go around, and even prior to that, of people just going over the horizon and see what happens. Like the Polynesians, they were like settling out the islands in the Pacific. That was able to happen kind of off screen, right? Like we didn't see them suffer, we didn't see them die of starvation, but someone on Mars, we would be getting video feedback, right? We'd be getting updates. We would be getting this. They couldn't fail in isolation and anonymity. We would see it plastered everywhere, which I think is a different kind of, we haven't really thought through what that would be like as a society to watch that happen.
So I have two comments about that, which I think you're spot on. Part of it is being honest, or not honest, but transparent about the risks of spaceflight. And so for example, we have 3 nations that are going to Mars, two of which have arrived, and then we're arriving on Thursday, right? We had to go through a lot of conversations internally to NASA before we actually started publishing videos like the 7 Minutes of Terror, because we didn't really want to talk about the risk at first, right? But then we began to realize that that's actually part of the story. If people understand those risks, then they understand, it makes it more amazing when you overcome it. But it also helps people to realize on those bad days when it doesn't go like you expect it to. There are unknowns, and that's part of exploring the frontier. The other comment I would make is that I started co-oping at the Johnson Space Center in 1986. So it was that while back, and my first 2 weeks, as a new instructor, when you're a co-op, they actually let you be an instructor of astronauts, which was totally fun. And the building I was in, there was a ground floor with flight controllers, second floor was instructors, third floor was astronauts. And so as a newbie, instructor still in school, my first day on the astronaut floor, was literally my senior instructor said, well, let's watch Challenger launch. And when we launched, I was up on the astronaut floor, and when everybody on that floor knew immediately that we had lost that crew. And I will never forget the screams from the staff that supported that crew, because they knew exactly what had happened. And everybody who was alive then has their story for that. The point being is that humans exploration is dangerous, and that crew knew about those dangers and risks. But it was only by taking those dangers and risks that they actually advanced space flight, and that's what it's going to take to get all the way out to Mars and really do it right.
Yeah, and I think the example you were pointing to earlier of being open with the risk. I mean, we've seen that again with companies like SpaceX, where they blow up on landing and they're like, great, we're going to try again. This may or may not work. And people get really into that, right? Particularly when there aren't lives at stake. But that's like it's engaging, because then you understand that it's not this, you're not seeing this veneer of perfection. You're seeing people, maybe it's easier to connect to something like that. I want to start talking about some potential change, like breakthrough technologies that could change some of these fundamental challenges. We're getting a lot of questions about nuclear propulsion, but also a few about artificial gravity. And both of these kind of, again, go to this fundamental thing of kind of like with radiation. If you can get to Mars faster, right? Because Mars is so far away, we've established. If we can get there faster, we can reduce that transit time. I feel like that starts to solve a lot of these really hard problems in terms of you won't need as much cargo, you won't need as much mass on the spacecraft, you won't need as many spare parts if you can just reduce that travel time to and from. So let's start with nuclear propulsion. There is a big report from national academies that came out last week that said this is in-space nuclear propulsion could be a kind of a game changer. What role does that play in your planning right now? And what could that, how could that help? What kind of improvements in transit time could you see from something like nuclear propulsion?
So I saw a great question they're asking about that transit time in the chat log, and I love that question. So I was, how to say this, I was a little skeptical about nuclear propulsion and the need to move in that direction. Except we kicked off a big study even before the national academies came out with their report. And I have to say, I really, I don't know that it's a prerequisite for sending the first crews out there. Again, if you view this getting going sooner than later, because there's two types of risks. There is the risks we know about because we have thought about them, and then there are the risks we don't ever know because we never go. And so if you really want to keep human beings alive or give them the maximum chance of doing that, you need to know about both sets of risks. And so if you can get going sooner than later with a simpler technology, I would assert it will teach us about the full risks we're dealing with so that we can focus on the ones that are most likely to hurt a human being on the way out there. And part of that means you go sooner than later, simpler. And so a chemical mission, which is entirely doable, we really know how to do that if you do what we call a conjunction class trajectory. So that's a 3-year trip. It's basically not 6 to 9 months out, 500 months parked in the Martian system, and then 6 to 9 months back. And so you're in space most of the time, not on the surface. And you may not even be on the surface that much. You might be in orbit around Mars, but you got to hang in the Martian system long enough for those orbits to link up. That's a 1,100-day mission altogether. We know how to do it. We know the radiation risks are there. We really could get going on that much sooner, because basically that mothership is next generation space station. We had got over 25 years, I think 25 years, I forget, we had an anniversary recently, where, and it is amazing what we have learned to do to keep human beings in space for long periods of time. And really we can leverage that heavily. And so by getting going sooner than later, we learn about those errors. But ultimately, you want to reduce the risk of the time. And as you were alluding to, the biggest thing, Casey, is to reduce the time. And there's basically two options. There's nuclear thermal propulsion, which is basically running hydrogen through a reactor and then spitting it out the back end. You wouldn't do that in the Earth's atmosphere, but once you're way up above the Earth, those reactors are what we call uranium-235. You could sit next to that reactor and no one would your Geiger counter won't even sense it until you start splitting atoms. So once it's in space, then you can run it. The other option is nuclear electric propulsion, which is a reactor. This is basically an electricity reactor, like what we have been doing on the surface of Earth, except it generates a lot of electricity. And then we use that, we send that electricity and we accelerate a propellant out through what we call electric thrusters, and they're basically creating a magnetic field that really is efficient and pumps out the stuff. We don't get as much oomph in terms of thrust out of those, but you can run those engines forever. And so what we're learning now is that it's nuclear thermal versus nuclear electric with an augmentation from chemical engines, or when you want to do a quick braking and that kind of thing. And these are looking really promising for reducing trip times down to 2 years. And then we're now doing trades. I think the National Academy had a slight lean towards nuclear thermal. We're not as convinced that it's that clear. And so we have a little more work to finish our report. But they're exciting for what they potentially offer.
Yeah, that's an interesting point, though. It's like if you need a breakthrough technology, you basically have to put the whole program on. That's like hold for magic to happen, and then once that happens, then you can go. You have no idea what it takes to make that happen until you start to do it right? Like it's easy to say, oh, well, all we have to do is do in-space nuclear propulsion, and then it's like, oh, it's actually a lot harder than we realized. Whoops. And then you've kind of delayed everything contingent on the success of this one new technology.
Well, and to amplify, Casey, you had delayed learning about those other risks.
Right.
And so you were fighting potentially not even the biggest risks because you never even found out about them. If you talked, I worked with the Expedition 1 crew, the first crew that went up to the space station, worked a lot with them. And if you would talk with them, they would tell you today that they knew it was going to be a flail, but they also knew that they had to get going on it so that we would figure out all the things we needed to do with actually operating and keeping a crew in space. And that speaks to those other risks that we really need to understand.
Right. So speaking to that, I just saw a question come in. I've seen a number of times. You kind of nice. I like how you're saying Space Station 2.0 to kind of basically be your mothership to and from Mars.
Yep.
Well, why don't could we just use the existing station or rebuild to print of the existing station and push that out to Mars as like a first step? Why could or could not we do that? What's the problem with that?
So the existing space station was not really designed for Mars, but it has taught us all the pieces that we need to know. I would assert there are some things we would definitely want to improve upon, but it wasn't so worried about mass. We've always had to worry about mass, but for Mars missions, you really have to worry about mass because every pound or kilogram, whatever units you want to use, that you push to Mars has a big multiplication factor in terms of propellant needed to push it out there. And so you would want to go through and really try to make those things more efficient. You would probably look at using inflatables. And then there's some equipment that really depends upon resupply from Earth. So I'll give you 2 examples. When we send up food to Mars, they go in trash. They go in plastic containers called food containers.
Up to the station, you mean?
Up to the space station. And then we just recycle it. And then there's tons of trash. It is amazing to see all the bags of trash, and then we put those into supply ships that are going to burn up in the atmosphere, and that's our dump, our trash disposal mechanism. You don't do that on Mars because you don't really have a way of disposing it, and really plastic becomes an incredibly valuable feedstock for 3D printing. And so you have to kind of go through and really change a lot of those ops concepts a little bit there. And then the other piece is that there's some equipment that does count on resupply too to really work. So for example, one of the most complicated pieces of equipment is what we call a urine processing assembly, right? That's a really complicated beast, and it's doing something that we don't do even in our homes, which is basically taking urine and making it drinkable. And it has a lot of parts. It has a lot of dependencies on stuff from the Earth. You're going to want a next generation on something like that so that it's not going to break on you on the way out on a 3-year mission where you have no option for coming home.
Yeah. That's something I really took from reading Scott Kelly's book, Endurance. And I really recommend that for anyone on this panel or watching this, for really opening my eyes into the unromantic aspects of being in space as a human. And he had to spend so much of his time fixing things that were breaking, cleaning things, and constant communication too with the ground, and lots of resupply. And I kept thinking about the implications of, kind of to your point about, we learned a lot about physiology and psychology of humans in space from the station, but there's a lot of problems about how do you make kind of an independently run spacecraft, that because you're going to be talking about a communications delay of anywhere from 15 minutes to half an hour. You have, you can't resupply it, right? You have to bring everything with you. What happens if something breaks, if that urine processor breaks, 30 minutes out, like, can they fix it that far away? And so some of those problems seem to be really hard that we can't test. Are those being worked into kind of immediate term, like at the Gateway Station? Are we trying to break free of an Earth dependence with some of these future projects coming up that'll help feed forward into a Mars mission?
So a couple points I would make on that is, yes, we are looking at those because we actually track how often things fail, and so we know the parts that really don't, that we can want to extend.
Do you know off the top of your head what's the most frequently failed?
No, but I would love to know. In fact, that's probably going to get me to look, because I want to know. But there's a whole range of things. So part of the question becomes, which parts do you have there, and which spare parts you do. Can you make the spare parts all do 3D printing so that you can actually print on the way with a feedstock? And then another question, which I think is really getting a lot of more attention now and needs a lot more attention. I've worked with the guy who does logistics for the South Pole Station down in Antarctica. And those guys will tell you point blank that it's logistics, 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 that you live and die by logistics. We're now reaching the point in figuring out Martian exploration with humans that logistics is really important. So you don't have, so one thing is you could you could actually stockpile stuff potentially in a Martian orbit, so that so then you're not worried about going for 3 years without any resupply. You're only going for the 6 to 9 months that they'd be on the outbound leg, and then you could rendezvous with parts. So it's learning to play all those kind of games in a very robust way that gives us options and flexibility. So that, and then there's a comment here from Heather about Mark Whitney, which I love. But it's learning that kind of flexibility and how to insert it in a different environment, not a space station environment, but in a real Martian mission environment. And that's the part that's going to take a lot of creativity. And I think we're totally ready to start looking at that.
I'm going to combine a couple of questions that I'm seeing here coming in. Of kind of this opportunities for international. Does NASA see international collaborations as a critical aspect of a human mission to Mars, and kind of what might that look like? And then to kind of extend it a little more broadly, is there an issue with ownership? Who owns Mars, and is NASA and others free to go wherever they want? Is there any issue with commercial companies looking to exploit resources? Is there any of those on the horizon that are going to be a problem?
So love that question. Thank you. I would I think it's true that every single mission to Mars, I'm talking robotic missions right now, are all multinational. So you will typically have one country or space agency be what I would call the trunk partner, maybe. They own the spacecraft, and then, but there are a lot of countries that are actually contributing instruments to this, and that's really critical for not just reducing cost, but actually for increasing participation and knowledge gained on these missions. And every one of them is that way. I happen to be working on a mission called the International Mars Ice Mapper mission, and that's actually a different pattern. In that mission that we're working on, we just signed an agreement between JAXA, CSA, JAXA, and OSI and NASA to actually go send a mission out there. Each agency on their own does not have to do it, but each agency is actually contributing major chunks. The mission doesn't fly without these contributions. And the key here is that this is a new paradigm. It's actually patterned after the ISS paradigm, where countries are there's a real interdependence in terms of pulling it off to make something that would not be possible otherwise possible. And we really, all of us who are working on this across those 4 agencies, and there could be additional agencies soon, actually strongly believe this is the pattern that we need to be moving towards for those human missions, where you really are doing partnering and leveraging that experience that is significant across the planet. I mean, the Japanese, just for example, just return samples from an
Hayabusa,
asteroid that is
yeah, exactly. Well, not the Hayabusa was the spacecraft. They were you put me on the spot. I just forgot the asteroid name too.
But
we're going to be called out.
The engineering on that is outstanding, and I'm just saying there's tremendous experience now across the planet. We're collectively crazy not to work together to do this, and it's also important to realize that that applies to the commercials too. You know, the SpaceX is like the largest launcher that there is on the planet, right? I think right now, and they actually own. I just read the other day they own 1/3 of all the satellites in orbit around Earth right now. And when you have those kinds of capabilities and you start all working together, and there is a complexity with that, really incredible things become possible. And that and the agency, NASA, strongly believes in that kind of partnering.
Yeah, Ryugu, someone was kind enough to remind me, is the asteroid.
Thank you.
And I have your Mars Ice Mapper slide up right now just to kind of show a little bit about it. And it brings up this other question, though I guess I first want to say, just to build off what you were saying, this international cooperation and alliances, really, I always say that that's like the best spin-off that NASA's ever had, is this forming and tightening peaceful cooperative opportunities with like-minded nations and strengthening those ties together. That's an incredible spin-off, that statecraft of peaceful exploration. But something like Ice Mapper here.
Oh, go ahead.
Yeah, go ahead.
No, finish your idea, please.
So Mars Ice Mapper here, the idea of Mars Ice Mapper is that it's kind of what it says, right? It's going to look for near surface ice deposits on Mars, with the idea that it can serve as potential in situ resource utilization for astronauts on the surface, right? You can use ice to make rocket fuel, you can drink it, you can, do lots of things with it. So you don't have to bring everything with you. Someone had raised some questions about how do we talk about planetary protection, right? When we're actually, so the areas of the most biological interest on Mars are exactly where Ice Mapper would be looking, right? This near surface ice. So how do we, is there a tension between human exploration of Mars and planetary protection? And how do we resolve that tension?
I love that question. Thank you. So how to say it this way. It's a really important thing. So planetary protection, for those who don't, there's 2 concerns. There's one that we're going to Mars to try to find life, right? So we don't want to garb it up with the human biology. So that's number 1, right? And secondly, there's what we call backward contaminations, which is when all of a sudden, if there is life there, we don't want to infect the crew that's there or affect the people back on this planet with that biology. So those are 2 pieces of it. I'm not so worried about the planet here so much, because the crew, when they go, is actually in quarantine, and if they've been exposed, you're going to know it. Now, what you might do when they get back is another matter, but I think we would be safe on that part. But protecting the science, we have actually been exploring Mars for 50 years now, which is really incredible to think about. We have found tantalizing signs where you find methane and that kind of thing, that there might be life there. But Casey, I love the point that you're pushing on, which is that if it's there, many believe that it is probably at or near the ice in the subsurface because of the radiation environment there. And so the question is, if you want to find it, this is a frontier. There are not any guarantees here, but if you want to find it, that's where you go look. Because that's where the really cool answers are. And it's like those other risks that we talked about. We have to manage them as smartly as we can. But if that's the amazing discovery, if you can find that life actually evolved on another planet, that's transformational in terms of our understandings about ourselves. And so the trick becomes, how do you do it safely? How do you do it in a way that protects the science that we're after? And there are ways to do that. And we have been working very closely with the Planetary Protection community, and they are interested in doing this. I mean, they want to do this. They would like to do it in a controlled fashion, maybe robotically first, but they know that when human goes. And I would just add one other thing. Having watched the Mars exploration program for a while now, which is that it may require the flexibility and versatility of a human astrobiologist sitting on the surface of Mars to actually figure out the right place to drill. You know, when Jack Schmitt on Apollo 17, he was the only scientist, a geologist that went on Apollo 17. And having him there was transformational, I would argue, in terms of actually understanding, you know, potential geologies to capture. And if you can imagine an astrobiologist that she's sitting right there, she says, that looks weird as hell. That's where we ought to be during a core sample. That's what you want to know, and have that flexibility. And I hope to God that on the first mission, an astrobiologist is on the crew.
I had just done kind of a mission summary for the Planetary website about Apollo 14, which always got a lot of criticism from geologists because they didn't do a good job cataloging where they got their rocks from. Like they said, like, oh, we collected this rock here. How do you know which one it is? Oh, it's got a unique shape. And the geologist came back and said, all rocks have unique shapes. And it's because they weren't trained geologists, right? And so poor Al Shepard and Ed Mitchell, you know, they tried. But yeah, having Jack Schmitt there on the surface, trained geologist, makes a big difference. And maybe it's no accident that Jack Schmitt's rock is sitting in the Oval Office right now from Apollo 17. So yeah, to your point, the having a scientist there to kind of make those on the scene decisions is really critical. But again, this idea of this planetary protection, I'm fascinated by this tension though, because I think there's also this broader ethical argument, right? That if there is something there, you have to be really careful about introducing Earth biota into that environment on the off chance it could wipe it out. I remember John Grunsfeld, the Hubble, you know, repairing the Hubble astronaut and ex-head of SMD, talking about, I never thought about this, but of course, right? No spacesuit is perfect. So every spacesuit's just like leaking viruses and bacteria from people, right? Because we're very rich collections of those wherever you go. And so how this always made it kind of this argument. I feel like it's actually a really good argument for sample return robotically right now, prior to when humans go, right? Because we have actually an ethical responsibility to try to understand the Martian environment and potential habitable environment before we send humans that could potentially change that.
So I love that point. A couple comments I would make is that I personally, there are a number of people who talk about, you know, once we send an ice mapper, know where the ice sheets are better. We know that they're there. We just don't know how close to the equator they go, and that's an important question because it's really hard to operate up further away from the equator. But after we know that, there is a lot of people who are very interested in the idea of a special regions explorer, which would be a drill that would go down there. And that would be your control data point, if you will, where you access the ice and hopefully control and return those samples. You know, Mars sample return is not a one-time deal. You're ultimately doing it. And so maybe the crew goes into orbit for the first mission for all the reasons that I described originally. But the other thing they do is they rendezvous with ice cores that were launched off the surface so that we can have a controlled set of samples before we send humans doing there. And then when humans do go, they're not all bad, right? Because they bring the versatility, you know, all the things that we're there. At Antarctica, we actually look for extremophiles, which is basically organisms that are living in rocks and in very harsh environments, and we manage that, right? Because we have rules. We know where the human effluents are going downwind. Mars has a wind. We can learn those predominant winds. We can learn to keep areas that are clean. Mars has more surface area than the Earth has surface area because we have so many oceans. And so the point being is that we can keep clean areas that are pristine and other areas that we may be able to be willing to tolerate a less clean environment, knowing that the radiation environment is going to help cleanse and sanitize. We have to learn how to manage those risks. But, you know, finally, I would add, you don't learn by not taking risks, you know. And so we just have to learn how to manage them in a way that doesn't sacrifice the science, doesn't, you know, put the biology of another planet at risk unnecessarily, right? And then we can, you know, I'm confident that with all the smart people on this planet, you know, we can figure out those challenges.
I'd say that's a good optimistic take. So we're going to start wrapping up here. We got about 5 minutes left. So I wanted to just address where we are right now, which is we're talking about Mars, but this is in the context of the Artemis program, right? With NASA going back to the moon. And, they've been very careful to say moon and then on to Mars. And so I'd love for you to talk a little bit about how is Artemis feeding into Mars planning right now? And what do you see as the opportunities in this near term next decade for human spaceflight at the moon? How is that going to help our efforts to get humans further out to the red planet?
So it helps in a number of ways. I'm not sure I would say it's a prerequisite for going to Mars, but I do think it helps in a number of ways. So let me give you some examples. We talked about the suits, the current 350-pound suits that we have right now, they don't work on dusty planetary bodies. We have to get the mass way down. We have to really be comfortable that we can get in them and not have the joints get covered with dust and that kind of thing. Moon's a perfect, moon's actually a more harsh environment. So if you can make it work on the moon nearby, you will be able to make it work on Mars. Another obvious one is rovers. We need rovers that work really well. They need to do all the things, Casey, you alluded, including those wheels, so that we can make sure they really work before we ship them 220 million miles away and expect them to work on Mars for long periods of time and robustly. And that's a perfect use of it. The Ascent modules should be very similar. That you could see a lot of feed forwards. The entry, descent, and landing systems won't feed forward a whole lot because Mars has an atmosphere and the moon does not. And so that's a different problem. Staying in space, unfortunately, on the Gateway, we're not going to be, the stays are not real long as currently envisioned, but maybe we grow to that, and maybe we grow to that, whatever that Gateway is. Maybe that is the Mars transfer vehicle, over time. And so, we can learn to work in that, and we will learn a ton about operating in that high radiation environment and really learning about the logistics questions. The communications piece also feeds forward very nicely. And so if you crack that nut at the moon, you know what, it's probably the same daggone thing, because communication satellites around the Earth tend to operate differently than they do around the moon. For one reason, because we have magnetic fields at Earth that we don't have at the moon or Mars. And so those kinds of things do feed forward and buy down risks and bring that timeline closer and closer for the first humans heading out there to Mars, that is.
Yeah, it's interesting. Like we've seen, as you said, Mars, the moon isn't a requirement, but at the same time, I see the opportunity I always look through a political lens or a policy lens.
Yeah.
And if you can build a coalition dedicated to getting people beyond low Earth orbit, right? So we've had this coalition for almost 40 years in low Earth orbit for the International Space Station. We could build something at the moon. You start building that coalition with the basic infrastructure, that heavy lift vehicle, the kind of the key pieces of hardware that you said that have these applications at Mars. There's a coalition to build and sustain those. And then once you establish that presence at the moon, you can take that coalition and just extend it further. And so it may not be maybe the most efficient way, but political coalitions aren't designed to be efficient, right? That's not like why they're there. Right. But they can be really stable.
No, and it's a stepwise function, and you learn how to bring in commercials in ways that we haven't done before. There's a lot of things that happen, and there are also objectives that are not just Mars oriented, right? And you have to factor those in too. Those are real. I was just speaking from a Mars mission standpoint. In the end, on Mars, you can do all the risk mitigations you want to do in low Earth orbit and in the Earth-Moon system. But in the end, there's going to be a political decision that says, you know what, humans are ready to go 220 million miles away, because when you light those engines, you're gone. You're not coming home.
Yeah, you can't stop midway to Mars and turn around and come back.
That's right. You're not stopping midway. And that's a policy decision. So I'm just saying, that's the reality. But in the meanwhile, those kinds of opportunities in the Earth-Moon system do buy down, the development times, which is great.
All right. Last question in our last 60 seconds here. A lot of people asking, when can we see this human to Mars mission? When is it going to happen? Not to put you on the spot.
So I answered this in the chat log or in the questions, and when I look at the breadth of activities across not just the United States, but across all the countries that are doing this, and I'm actually a secretariat for the International Mars Exploration Working Group, which is 26 countries or space agencies that are working on this. And I'm pretty familiar with commercial activities underway right now for other work that we're doing. There is no reason why humans can't be going in the mid-2030s out to Mars, in my opinion. The pieces are forming up, and I always say that in the short run, things seem to go slower than you want them to. But when you have that kind of talent and that kind of capability emerging, don't bet against the medium and long term. And before you know it, 15 years from now is coming upon us real fast. And I just think when I look at, and the biggest reason, frankly, is that kids that are in school today, they already accept it as a reality. And when you accept it as a reality, you know what? It has a way of becoming a reality.
That's a great statement to end on. Rick Davis, Assistant Director for Science and Exploration at NASA Headquarters, Science Mission Directorate. I want to thank you so much on behalf of everyone here at the Planetary Society and at Planet Fest. Thank you so much for coming and talking about Mars with us today. A lot of people saying they could listen to this all night. I honestly could probably talk with you for the next 6 hours or so about this, but we'll have to call it here.
Well,
so thank you for being here.
Thank you, and thank you to everybody online for all your wonderful questions. It really is fun. That's how we're going to learn, is by everyone asking those kinds of questions. So thank you.
Yeah. I appreciate your time. Thanks again, everybody.
Thanks to all of our speakers for sharing their expertise with us today. During your short break, stop into our exhibitor section. We have some tremendous supporters who have helped make Planet Fest possible. Click on exhibitors on the far left in Whoville to see their profiles. Coming up next is our final session that will be detailing the 7 minutes of terror. You don't want to miss this. Please click on the agenda to the far left and choose the session title to get you connected. Thank you and have a great afternoon.